back for part 2 of take 2 of linear equations. Um, what makes this one weird is it doesn't look like the ones that we're used to, right? We're used to sine x equals whatever, cos x equals whatever, tan x equals whatever. This isn't that, right? So the first thing that we might be interested in doing is making it look like that. Uh, we're used to maybe just this part, although this is weird, but we'll get to that. Subtract 1 from both sides, divide by the square root of 3. No problem, okay. It doesn't deal with this weirdness, but I'm going to worry about that weirdness after we get rid of this on that side and divide by the square root of 3. And now this is a special angle. Right now, at least, I can see, what I'm talking about. In fact, because I haven't seen this, I'm going to use a problem-solving strategy that's very common in math, and that's solve a simpler problem. If something bugs you, get rid of it for the time being. So maybe I'll just call that whole thing theta. And now this is happy place, right? I can do this. Well, maybe not that happy of a place. And the idea is, what I've actually done here mathematically is I've made a little substitution, right? This looked bad to me, so I substituted it in for something that's simple to me, or at least simpler. And now I'm going to think about my my diagram calculator thing. Diagram, that's what I'm up against here. I want to do a diagram. And again, it's not a calculator one because this is one of the angles from my chart, right? Instead of diagram calculator think, this is, I know what the raw is here. This is a chart, and this is pi over 6. Look it up if you're not sure. Well, where are the terminal arms of these angles theta? And notice I'm thinking about theta now. Well, where is the tangent negative? Where is it negative? This is, oh, soup turns cold. The tangent is positive here and here, so it's got to be in this quadrant or this quadrant. And there we go. And remember, the related acute angle's got to be the same in both spots. Ra, the related acute angle. This is pi over 6, and this is pi over 6. And now I can see my two solutions theta. There's theta. I'll call that theta 1. You say, Mr. Restall, it's this thing. It's x that we want. Well, hang on. I know. I'm getting to it. I'm solving a simpler problem. So there's theta 2. And now I can at least state that my solutions theta 1 and theta 2. So here, theta 1 was almost pi. So this is pi subtract the related acute angle, pi over 6. And again, for funsies, I'm going to put in the all solutions business. Okay, so I'm going to put in plus 2 pi n. Just, again, for funsies. Now, a little bit of work to do here. Theta 1 is, that's 6 pi over 6, and I think some of you are getting good at counting by these. So there's all the solutions, or all the solutions there. But hang on, it wasn't theta that I wanted. It was x. So how do I deal with that? Well, let's get my solutions back in terms of x, and I'm going to call this x1. Thin. Make it thinner. x1 plus, minus pi over 3 is equal to that angle. And I'm leaving all my solutions in here for a reason we'll see very soon. Well, easy. I can just solve that by booting that up to the other side. It's like terms with this. It doesn't have an n with it, so I'll put it with this piece. 5 pi over 6 plus pi over 3. That's kind of like the principal solution there. And I get common denominator again. 2 pi over 6. This is 7 pi over 6 plus 2 pi n. There's my principal solution between 0 and 360. and then I can get all solutions. Okay, well that's only the solution that went with theta 1. I also have to do this whole shindig again with theta 2. So some smartboard magic, and I apologize if you're squishing, but not that much. I don't apologize that much. All right, I'm going to try and squish the other solution in here. Well, this is the think part, right? Where is the second solution? It's in quadrant 4, my theta 2, and I'm not dealing with x's, right? Because theta 2 was in the fourth quadrant, which is 2 pi subtract the related acute angle plus all of the solutions, and I'm bringing that along for a second there. And I get a common denominator, 12 pi over 6, and I get this idea here is we're getting used to this. This is 11 pi over 6. Some of you can sort of see that and write down 11 pi over 6 straight off. That's fine if you can. Now notice, there's my solutions in terms of theta, but let's solve the problem I was asked to solve. Substitute back. And same deal. Move the pi over 3 over to the other side. I'm going to actually move this over. Hopefully this doesn't scare anybody. Move this over and write it in common denominator, all in one step. Hopefully that wasn't too spooky. Put those together, and actually something weird happens here. Because all my solution set then, therefore my solution set, I could write them like this, right? 7 pi over 6 plus 2 pi n, and then 13 pi over 6 plus 2 pi n, 2 pi n. But what are my principal solutions? My principal solutions, one would say, okay, it's these things, right? 7 pi over 6. But notice what happened. When I added the pi over 3, this isn't a principal solution anymore. This actually got bumped into the first quadrant. This 13 pi over 6 is 12 pi over 6 plus pi over 6. If I wanted to write this as a principal solution, I'd have to bump it up into the first quadrant and write pi over 6. One way to think of this is, what value of n would I have to pick? What value of n would I have to pick so that this whole answer here, this whole answer is somewhere between 0 and 2 pi? Well, if n equals -1, that's when I get 13 pi over 6 minus 2 pi, which is 12 pi over 6, and there's where I get my pi over 6. Do you have to show all this work? No. If you're able to understand that this is pi over 6 straight from this, that's fine. Now, the textbook does a tricky thing, and instead of writing this, 13 pi over 6, they'll rewrite this as pi over 6, and you'll wonder where the heck they got pi over 6. Well, they're just writing the general solution with a principal angle there. Okay, there are those two solutions. That's it. Dandy. And let's go on to the last one. And the last one things get a little weird. There's the homework. I'm going to need, hopefully you have this homework on there. I got to get rid of it because it's in the way. All right. Get rid of that. And again, we've got one of these ones where there's junk all over the place. It looks like it's a transformed trig function, and it is. But we would like to see something like cos blah equals whatever, right? That we can solve from grade 11 and from earlier on. So we are going to do the same thing. We're going to move this around before we even get into the diagram calculator thing. So what do I mean? Subtract 2 from both sides. Equals 3, divide by 4. And it's pretty close to cos blah equals blah, but this looks weird. And in fact, again, because I'm kind of afraid of this, and this 3 seems weird, by the way, it's a little bit weird, I'm going to get rid of the whole darn thing. I'm going to let theta equal 3 times x minus pi over 6. and then I'm going to solve this simpler problem. Now, you might be, in this we can do, and we're going to do this. This might be thinking, you might be thinking this is a one of our special angles, but it ain't, right? Square root of 3, yeah, okay. No 4s. So this is just a plain old calculator, diagram calculator think, and this is a calculator question. How do we set it up? Well, diagram. And there's a couple of tools I have to get a good diagram here. One is the cast rule. Where is the cosine positive? The cosine is positive in the first and fourth quadrant, and that's fine. I like this thinking about it this way. I know the cos is the x coordinate. So when is the x coordinate 0.75? Well, x coordinate is 0.75 right about there. Right about there. And then I can get my two solutions, one in this quadrant and one in this quadrant. Okay, and there's my two thetas at least, and I'll put them on my diagram. This is theta 1. All the way around is theta 2. And now, how do I actually get what one of these is? This is when I use my calculator. Diagram, now I'm going to use my calculator. And I have to think about what my calculator gives me, actually. So here's my calculator step. And the calculator step is just do the inverse cos of 3/4, or 3 divided by 4. And remember, your calculator is in radian mode. Radian mode. And you should get, that's about 0.72. So what is this 0.72? Well, this is that first solution, and it's the related acute angle. So this 0.72 is the related acute angle. What I'm telling you about the think part is sometimes your calculator will lie to you. It'll give you a negative answer, or it might give you an obtuse answer. You really have to think about what it's giving to you. But this is the related acute angle. And in fact, I can start here by saying theta 1 is equal to 0.72. And again, for a reason we'll see very soon, I'm going to put in plus the 2 pi n. This is the general case, the general solutions. All right, well, there's my solutions in terms of theta, but let's substitute back and see what kind of madness this is going to be. This is x1 minus, okay. This doesn't seem so bad, actually. I could expand all this, but instead I know I'm going to have to divide by 3 at some point. I'm going to divide by 3, all right? So I'm going to divide both sides by 3, divide everything by 3, and something actually fairly interesting happens here. I get some number here, and I'll actually put that into my calculator in one step later. Later. This is not an exact answer, right? These are all calculator answers. What is this? What's going on here? What this is saying is the copies of my solutions don't happen every spin anymore. They happen every 2 pi over 3. That means they happen more often. Because that 3 in with the x represented a period change. If I were to graph this, instead of the normal cosine function, it would represent a period change. It means that the solutions occur more often. Well, there you go. That's what this little calculation meant. And off we go. And so add pi over 6 to both sides. And again, it goes with this part. And I'm putting this into my calculator in one step because I know it's going to be an approximate answer. And then bing, 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 calculator, you get about, I got about 0.76 for this. When you go 0.76 divided by 3 plus pi divided by 6 plus 2 pi over 3n. Okay, I'm going to leave that for now. I'm not going to write the general solutions yet. I'm going to go on and do theta 2 now. I got to get off my... I'm going to need to erase that because it's kind of in my way again. Erase that. And here we go. I'm going to pick up the pace a little bit. So theta 2. What's theta 2? Theta 2 is 2 spins, or not 2 spins, 1 spin, 2 pi, not 2 spins, subtract the related acute angle, right? Well, this related acute angle is 0.72. That was 0.72. And then I'm going to put in my 2 pi n. Calculator, just jam that into a calculator. Actually hit your pi button. 2 pi, subtract 0.76, and you get 5.56. About. All this is about approximate answers. And there's my answers in terms of pi, but when I substitute back in and solve the question I was asked to solve for x2, I'm going to get something that looks like this. And same trick, divide by 3. I'm getting used to this now, so I'm just going to write this as 5.56 over 3, and there's the period change, right? The period change that represented having the 3 in with the x. Add pi over 6 to both sides, and again, it goes in with the number part. This is a number part here. And calculator, jam that into a calculator, and it looks like it's about 2.38. And I don't need those. I didn't need those brackets there anymore. Yeah, I'm going to just put that back in as 2.38 like that. And there are my general solutions. So the solution set in general is 0.76 plus 2 pi over 3n and 2.38 plus 2 pi over 3n. Now, the principal solutions. The principal solutions, of course, are this one. But notice that when I add 2 pi over 3, I haven't went over 2 pi. So one of the solutions, remember the whole goal was to state all the solutions between 0 to 2 pi, right? But I can add a spin, and it's one of these squish spins that I mentioned up here when we were doing the diagram, right? There's the normal coast graph. There's and if I think about where is this transform graph equal to 5, there's going to be a bunch of solutions by the time I get to 2 pi. I'm adding just a little bit to get to another solution. So I actually have to get out the calculator and think of having n equals 1 here, adding 0.76 plus 2 pi over 3, and actually calculating that. That's, put that into a calculator, and I get 2.85. Right? Well, and I got to keep going. What happens if n is 2? Maybe that doesn't get me over 2 pi. And remember, 2 pi is about 6.28 about. So anytime it gets over 6.28, that's when I know I'm done. And I put in n equals 2 into that calculation, 0.76 times 4 pi over 3, and I get that little solution is about 4.95, and I keep going. For n equals 3, notice what I've got now. 0.76 plus 6 pi over 3. This is going to be too big, because this thing here is 2 pi. This is too big. And I can stop. And I can stop. All right. That gives me 3 principal solutions for this one general solution. And now, what about the second general solution? Well, I'm maybe going to get some more solutions. First one is 2.38, and then the second one I'm going to think of 2.38 plus 2 pi over 3. This is when n equals 1, and I do that calculation, and I get 4.47, and then I try it when n equals 2, and I get 2.38 plus 4 pi over 3, and this ends up with 6.5-ish. This is too big. This kind of seems strange because there were 3 solutions for the first one, 1, 2, 3, but I've only got 2 solutions for the second one. Well, it's because this angle is already big. This angle is already obtuse. If I try n equals -1, then I'm going to get 2.38 subtract n equals 1, 2 pi over 3, which gives me yet another solution. In fact, this gives me an acute solution, 0.29. And this is a lot to digest, but let's see if it makes sense. Here are all of the solutions. 3 that go with theta 1. And what does that say? 9.5. Can't read my own handwriting. 2.38, 4.47, and then 0.29. Does it make sense that this thing would have 6 principal solutions? Well, how many did cos theta equals, this had 2 solutions, right? It had 2 solutions, but then I squished it back by a factor of 3, right? Horizontal compression factor 3, period change factor 3. Does it make sense? I would have 3 times as many solutions. 1, 2, 3, 4, 5, 6 solutions. Absolutely, that makes sense. Okay, this is tough. This is a tough question, folks. This is linear equations take 2, part 2, and we also have a linear equations part 3, which will come tomorrow.